Okay, in this video I'm going to continue on with my tutorial videos on thermodynamics and statistical mechanics. This is video 18 and I'm going to discuss the multiplicity of an ideal monatomic gas, where monatomic means a single particle. And we'll see that the multiplicity for one dimension is the volume and position space multiplied by the volume and momentum space divided by actually h bar cubed or h cubed. Look, the factor of 2 pi is not very important because the multiplicities are so large. Now, in the previous few videos, I did a bit of I went down a side road and I discussed the Taylor and MacLaurin series. I discussed the binomial theorem, and I also discussed Stirling's approximation. So we want to come up with the multiplicity of an ideal gas with one particle. So what does multiplicity mean? It means the number of different states the particle can be in. So what characterizes a state for a single, let's say an oxygen molecule? Well, its position is important. If its position changes, so does it becomes a new state. Its energy is also important. But if we talk about energy, energy is not the most fundamental quantity, because we usually like to analyze energy in terms of velocity, or in a similar fashion we could use momentum, where we know that the energy of a particle, a non-relativistic particle, is p squared divided by twice the mass of the particle, where p is the momentum of the particle. So it should make sense that in general, like, what else can we think about? Well, there's no potential energy. We'll assume that there's no potential energy, so that doesn't affect it. There are no other particles which could interact with it, so it's a non-interacting particle. What else could there possibly be to change the state of the particle? So even if this isn't fully correct, let's suggest that the only factors which will change the state of the particle are its momentum and its position. So how do we find out the number of possible states? Well, we need to talk about the number of possible positions it has and the number of possible ways its momentum can be. So if that's the case, very generally we can say that the multiplicity of a ideal gas with one molecule in one dimension must be proportional to, not one dimension, but in 3 dimensions, must be proportional to the volume and position space. Because think about it, if you have one molecule and you put it in a box and you close the box, well, it has a certain number of states. Well, in other words, it would be the volume of your box divided by the volume of your particle, and PRTICLE. That's approximately the number of position states that are available. But if you double the size of your box, you're going to double the number of possible states. Or even if that isn't fully correct, let's just suggest that it's correct, because it sounds quite reasonable. So we're going to say that the multiplicity is proportional to the volume which your particle is inside in position space. And next we need to talk about momentum. So instead of characterizing, like, we know that we'll say E is p squared over 2m, so that means the energy of your particle is equal to p sub x squared plus p sub y squared plus p sub z squared over 2m, because we're talking about a single particle. Alright, so let's rearrange this. We're going to get 2me. Let's say, actually, by the way, let's talk about an average energy of the particle, to be specific, and we know later on we can say the average energy of the particle multiplied by the number of particles is equal to the total energy U, or the total average energy, but we in actual fact say that because the fluctuations are so small, we say that it's actually the total energy. So let's just deal with the average energy of a single molecule at the moment. So that's going to be equal to all of these to be squared. P sub x squared plus p sub y squared plus p sub z squared. But look, that really is just another placeholder, r squared, and if we look at that, that's just the equation of a sphere, where the radius of the sphere is the square root of p sub x squared plus p sub y squared plus p sub z squared. So if we want to look at momentum space, the energy of our particle and momentum can be analyzed by looking at the number of momentum states in a volume or surface area in momentum space whose radius is the square root of 2me. So think about this. There's in momentum space, there's p sub x, there's p sub y, there's p sub z. So we're saying that the momentum and energy are related. So if we plot a sphere whose radius is square root 2me, we'll say r is equal to square root 2me or square root 2me bar, we get some sort of a sphere. Okay, and the number of momentum states inside that sphere gives the number of possible momentum states, full stop, or the number of possible momentum values inside that sphere gives the momentum. Now, I understand that we're not talking about a volume really. We're talking about here I'm after saying it should be the volume in momentum space, but here I'm really talking about a surface area. So just bear with me for a second. It's not going to be very rigorous. So I'm going to leave the V sub p where it probably should be surface area sub p. All right. So right, there we are so far. So what we're saying is that the multiplicity of an ideal gas with however many molecules in 3D should be proportional to the volume in which the molecules are in, and the volume in momentum space, even though it is really a surface area. Alright, so how do we calculate these volumes? Well, particles are very small, or molecules are very small, so it's best to talk about these, talk about lengths and all that sort of thing using the de Broglie relationship. Alright, so if that's the case, we say that each particle has a wavelength. Okay, so here, let's say in one dimension, this is the length of my box. Sorry, it should be no p. There's the length of my box in one dimension. Well, my particle can occupy a lot of different states in here, where delta x, the position, we'll say the length in the box which has to be travelled before you come into a new state is delta x. So the total number of states, of course, is the length divided by the distance you have to move in order to change state. So this gives the total number of states in one dimension in position space. So let's do something very similar, and we talk about momentum space. We can talk about a length in momentum space. Okay, let's say if it's just in one dimension, say it's p sub x. Okay, let's say it's p sub x like that, and that means the radius is square root 2mu. The length of this would be 2mu. But once again, we talk about having some form of a wavelength. So this time we're going to talk about the length in position space divided by the change in momentum, or delta p, or the amount by which the momentum must change before it become a new state. So let's put both of those together and go back up to our initial suggested guess for the multiplicity, and we're going to get the length in position space divided by delta x times the length in momentum space, divided by delta p. But delta x times delta p, according to the uncertainty principle, is approximately h bar, or it's h over 2 pi. Is something like that. So I'm just going to say, but look, this 2 pi, it's quite small in terms of the numbers we're using. So I'm just for the moment going to call it h. So that means we have L times L sub p divided by h. Okay, that's in one dimension, of course. So if you want to actually use this, if you want to scale this up into 3 dimensions, as I've actually said here, then we need to get rid of all these L's and make it, we'll say V, we have Vp divided by h cubed, like that. So that means that the number of states for a monatomic ideal gas in 3 dimensions is proportional to the volume of the in position space times the volume of momentum space divided by h cubed. Okay, and in actual fact, for the moment, I'm just going to say it's equal to it. Alright, so that's all I've got to say about that. In a future video, I'm going to discuss the multiplicity of an ideal gas with multiple particles. So thanks for watching. Please pass on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.